right time. Then you know, watch the right time. Right. This is off now. The speaker is off. On. So yes.
Are you all right?
Yes, I'm fine.
Hi, Samit.
Hi.
Hello,
Yeah.
how are you?
Good, good,
We'll,
good.
we'll start in another 2 minutes or so.
Yeah. Sure, sure.
Good morning, Pastor Jagatap. It's good evening, sorry,
Yeah,
good morning.
good evening, good evening.
Yes, we'll starting in another 2 minutes.
Oh, sure.
Okay.
So, Professor Kosterlitz, we want to start now. So, before we start your lecture, I will give a brief introduction about today's lecture and I will introduce you.
Okay, I'm ready.
Okay. I will just take 5 minutes from you before you start.
I'm
So,
sorry, what?
I will take 5 minutes to give an introduction of the lecture.
All right.
Okay. So, good evening, everybody. But of course, very good morning to the distinguished speaker joining from Brown University, USA. On behalf of the SN Bosch National Center for Basic Sciences, I am very happy to welcome you all for the 15th C.K. Majumdar Memorial Lecture to be delivered by Professor John Michael Kosterlitz, Brown University. Under the Visitors and Linkages program, the center has a mandate to organize several memorial lectures in different areas on the memory of legendary Indian scientists like Satyendranath Bose, C.K. Majumdar, G.N. Ramchandran, and S. Chandrasekhar. Today's memorial lecture is being organized as a tribute to late Professor Chanchal Majumdar, the founder director of the center, and this lecture series started from 2001, a year after the sad and untimely demise of Professor Majumdar. As the first director, Professor Majumdar had outstanding contributions for creating this institute, which is in its present form, and it started from designing of buildings, planning facilities, creating a culture for teaching and research in the frontiers areas of physics. Professor Majumdar was a renowned condensed matter physicist. He worked for his PhD with Professor Walter Kohn, who received the Nobel Prize in Chemistry in 1998, and Professor Maria Gope-Mayer, Nobel laureate in Physics in 1963. Of course, he preferred to return to India to serve the Indian science and was initially at the Tata Institute of Fundamental Research and then at University of Calcutta. Professor Majumdar's significant contribution to condensed matter physics is very well known through his groundbreaking work on Kohn-Majumdar theorem and later another pioneering work as Majumdar-Ghosh model, an extension of the Heisenberg model, which serves as a stepping stone to a broader understanding of complex spin models. Today we are very happy to have with us Professor John Michael Kosterlitz as the 15th speaker in this lecture series, who will be speaking on topological defects and phase transitions. We are grateful to you, Professor Kosterlitz, for agreeing to deliver this lecture online, which we are planning for the last 1.5 years. Initially, we thought we'll have a physical visit in the summer of 2020, which of course didn't happen because of obvious reasons. So, before I welcome you all and ask the speaker to start his lecture, I will have the pleasure to introduce today's speakers briefly. John Michael Kosterlitz is a British-American physicist. He is a professor of physics at Brown University and is the son of a famous biochemist, Hans Kosterlitz. He was awarded the 2016 Nobel Prize in Physics along with David Thouless and Duncan Haldane for work on condensed matter physics. He graduated from Cambridge University earning a BSc in Physics in 1965, an MA in 1966, and received a DPhil from Oxford in 1969. He was a postdoctoral fellow at Torino University, Italy in 1970 and at Birmingham University, UK from 70 to 73. There he met David Thouless and worked together. They did their groundbreaking work on phase transitions mediated by topological defects in 2 dimensions. He was a postdoctoral fellow at Cornell in 1974, on the faculty of Birmingham from 1974 to 1981, and professor of physics at Brown University from 1982 to present till now. He focuses on the application of topological ideas to the theory of phase transitions in 2-dimensional system with a continuous symmetry. Professor Kosterlitz's theory has been applied to thin films of superfluid, helium-4, superconductors, and to melting of 2-dimensional solids. Experiments on 2-dimensional layers of colloidal crystals agree with the theoretical predictions in quantitative detail. This work was recognized by the Lord's Ensemble Prize in 2000, memberships of the American Advancement in Science in 2007, by the 2016 Nobel Prize for Physics, and elected to the Fellows of National Academy of Science in 2017. With this brief introduction, I now invite Professor Kosterlitz to start his 15th CK Majumdar Memorial Lecture. Professor Kosterlitz, you can share your screen and start speaking.
I hope I thought I was. Am I sharing screen?
No, I cannot. You have to share your screen again.
Just hang on a minute.
I think your screen is minimized probably.
I don't understand. I don't understand what's going on here. All right, let me try again. Jeez.
Probably your screen is minimized, so you have to click it once more so that.
Does it work now? I mean, according to my computer, I'm screen sharing. Can you see my slide?
So you can stop the sharing and then again start the sharing.
Maybe you have to stop sharing and then start sharing again. I don't see the screen till now.
I think you can, yeah. Now it's coming.
Probably
We see it. We see it.
You see the first slide? All right.
Yes, sir.
Though this is
Okay,
the
good.
second slide.
Yeah, we
can see.
Then I can leave.
Yeah, I think
Yes.
so.
Yes, we can see. Right.
Okay, right. So now, let me start. I'm very honored to be asked to give this prestigious lecture, and I hope that my this computer system works out, because I've had trouble with this system before. Now, as you heard in the introduction, my talk is called Topological Defects and Phase Transitions in 2 Dimensions, with a subtitle or alternative title, A Random Walk Through Physics to a Nobel Prize. Because when I was doing this work, physics wasn't really my main interest. My main interest was actually climbing mountains, and so I did physics for 4 or 5 days a week, and was in the mountains for the remaining time. So, and during my time doing physics, I was sort of wandering from one subject to the other until I found something which I liked. And when I met David Fowlis in 1972, I think it was, he got me interested in phase transitions, and he suggested this problem to me about trying to explain phase transitions in 2-dimensional systems, in a system with continuous symmetry like a helium film. And basically, so since I didn't know much in the way of solid state physics, I wasn't too much of a disadvantage, because nobody else knew much about it either. And so there was this major conflict between theory and observation, because theory, with the interpretation due to the Russian school, Lev Landau and so on, who said that a low temperature phaser, will have long range order. But there was a piece of theory, which is very simple but rigorous, which said that there's no long range order in these systems in 2 dimensions. And therefore the conclusion is that there should be no low temperature phase. Or in helium films, there'd be no superfluid phase. But experiment observation clearly showed that there was a transition to a separate superfluid low temperature phase, and so this was a small conflict that needed sorting out. So that was the problem that David Thouless suggested to me, and so I was completely ignorant, but I got very intrigued by this problem, and in my younger days I was sufficiently active that I could actually do the calculations and get them right. Well, I think I got them right anyway. So let me start now and go back. Remind you what the situation in two-dimensional systems in the 1970s was. Well, it can be described, basically they can all be described by a set of, in terms of a magnetic language, and they're all summarized by this Hamiltonian, where which nearest neighbors interaction between n component spins, unit length spins. And so at the time, the n equals the one component system had been solved, and there is in 2 dimensions, and there is a phase transition, because this is the Ising, two-dimensional Ising model, and Onsager solved this back in mid-1940s with an exact solution, and yes, there is a phase transition. But however, for higher spins, 2 component spins, 3 component spins, and so on, nobody really knew anything, except that there was no long-range order, which immediately, if you combine that with Landau's prediction that there should be long-range order in low temperature phase, there could be no transition. And so for the Heisenberg model, which a 3-component spin, the answer was, numerical work showed there probably wasn't a transition. And certainly, if you take the number of spin components to infinity, this is the so-called spherical model for which there's an exact solution, and then there is no phase transition in a 2-dimensional system with short-range order. But this intermediate situation, a 2-component spin system, which can be mapped onto the theory of superfluid helium films, the theoretical situation was rather uncertain. And so I suppose that the best thing to say that in the 1970s, the conclusion for that particular system was maybe there's a phase transition. But this situation needed further study, especially for the 2-component model, which I said maps onto superfluid helium films and so on, and 2-dimensional superconducting films. And this was the problem that Thouless suggested that he and I looked at. So we did, and oops, I'm going the wrong way, sorry. And now, so that in the mid-70s, well, so I just summarize some of the literature of the time, and these are the papers which Thouless and I wrote on this subject, and which actually led us to a Nobel Prize in 2016. Now, these journals are not the most, they don't have the greatest, impact factor, and they're respectable journals, but they're not the most famous ones. But nevertheless, pieces of work, even in journals like this, can actually turn out to be important. And so I was very, very pleased to find that, these papers ended up being important enough to catch the attention of the Nobel Committee. Now, so I thought I'd tell you a little bit about what the situation was. Now, one of the important experimental papers, which was published in 1972, I beg your pardon, was by Chester, Yang, and Stevens. And this was the experiment they were doing was they had a resonant crystal, with a particular resonant frequency, and they absorbed a thin film of helium onto the surface of this crystal. Now, this film was, just 1, 2, 3, 4 atomic layers thick, and so naively you would think that the helium atoms would simply stick to the surface of the crystal, and when the surface of the crystal vibrates, the helium atoms will simply move with the crystal, and therefore all they do would be increase the effective mass of the resonating body. And so, you can certainly calculate the resonant frequency, and basically what happens here is that the straight solid line is the theoretical prediction. On the left, on the vertical axis, is the reduction in the resonant frequency as delta F. And the horizontal axis is plotted a function of the pressure of the gas, the helium gas in equilibrium with the crystal. And this is basically linear in the coverage of helium on the crystal. And so the straight line, the solid straight line, simply says that the resonant frequency decreases as you increase the amount of helium that's absorbed in the crystal. And so one would expect that as the pressure of, the vapor pressure of the gas in equilibrium with the crystal increases, that more fluid will be absorbed in the crystal, and therefore the resonant frequency should decrease according to the straight line. And for small coverage, it does. You can see that the experimental points, after a few little bit, follow the straight line for a while. But then at some critical coverage, suddenly there's a major deviation from the measured frequency, resonant frequency, to the expected resonant frequency. And so the amount by which the experimental points deviate from the expected theoretical solid line is basically proportional to the amount of fluid that has decoupled from the crystal. So what's happening here is the crystal is vibrating, and a little bit of the fluid vibrates with the crystal, but then the rest of the fluid decouples from this and simply doesn't participate in the oscillations. And so this phenomenon, this deviation from the straight line of the experimental points needs some explanation. And the simplest, most obvious explanation one can give is that part of the helium fluid has gone superfluid. In other words, it's decoupled from the substrate. However, remember the theory, due to long-range order and so on, said that there's no distinct flow temperature phase, and therefore this phenomenon needed some explanation. Now, let me summarize a little bit about two-dimensional systems and just introduce in a few words what what topology means in this context. Now, we have a set of, so let's think about the one-dimensionalizing model for a moment. And what we have here is a set of spins, which are, say, plus or minus 1, and the spin configurations can be classified in one dimension by the set of the domain walls, or the places where the spin direction changes. And these domain walls, if you wish, in one dimension are called topological defects. And there is a theory of what goes on in one dimension with long-range interactions. That was a set of papers by Phil Anderson and Gideon Yuval and so on. And basically, those are the papers from which I learned about the renormalization group. However, more interesting, at least according to Thouless, was the planar rotor model, where the spins have two components and you assume they're fixed length. And so the spins are defined by a single angle, which I can call theta. And one can alternatively rewrite this in terms of an order parameter field, which I can call psi, which is simply the x component of the spin plus I times the y component, which is simply the magnitude times e to the I theta, with where theta is defined at each lattice site. And of course, the Hamiltonian, which is just basically minus SI dot SJ, nearest neighbor interaction, is invariant when the phase of the order parameter theta changes by a multiple of 2 pi. So, in other words, where theta goes to theta plus 2 pi n, where n is some integer 0 plus or minus 1 plus or minus 2 and so on. And the topology of such a system is a torus, and this implies that the global excitations are these so-called vortices. And you've all seen a vortex. For those of you who've taken a bath, you know that when you pull the plug out and the bath water drains out, it swirls round and round. And what you're looking at when you look at this is it's a vortex. And so if I take add up the phase differences as I go round the center of the vortex, this has to change in the superfluid case, has to change by a multiple of 2 pi. In other words, the integral around some closed contour is a multiple of 2 pi. And so, now the next thing to do is to estimate what the energy of such a vortex configuration and the entropy is. Because if these vortices can exist freely in equilibrium, then clearly the system is going to be disordered. But if there are no vortices, if they're forbidden for some reason, then the phase will be different. And so you can calculate the energy relative to the stationary state, the ground state of the configuration where the change in the angle as you walk around some contour is just proportional to the logarithm of the system size. Now, to be precise, if the exchange constant is J, the energy of a single vortex is just pi j to the logarithm of the system size. Now, of course, the entropy of such a configuration, according to Boltzmann, is simply Boltzmann constant and the logarithm of the number of possible configurations. Now, if we take a lattice with a lattice spacing of A, the number of possible positions of the center of the vortex is simply L squared over A squared, and therefore the entropy is simply K Boltzmann's constant, the logarithm of L squared over A squared. And the free energy, now, of course, in statistical mechanics, the central quantity here is the so-called free energy, which is simply the energy itself minus temperature times the entropy. And so we have pi j minus 2 kt times the logarithm of the system size divided by the microscopic length scale. And this, if at low temperatures, where pi j is larger than kt, clearly there'll be the free energy will be proportional to the logarithm of L over A, with the proportionality constant being positive, so that the probability of such a configuration, according to statistical mechanics, is just some e to the minus beta f, or f over kt, and this will tend to zero as the system size goes to infinity. In other words, this L over A goes to infinity. And so if this parameter k, which is just basically in the magnetic language is J over Boltzmann's constant times temperature, so then the probability of a vortex being present behaves like L over A to the minus pi k minus 2. And so if this parameter pi k is larger than 2, this goes to 0 as the system size goes to infinity. In other words, no vortex, the probability of a vortex being present is infinitesimal. But if pi k is smaller than 2, the power is positive, and therefore the probability of such a vortex being present will be 1, because it'll be there with probability 1. And therefore one has to interpret the high temperature phase as being a phase with a load of vortices, and of course the vortices will disorder the system, and so one can interpret these trivial calculations as there being a critical value of the exchange interaction divided by temperature, of course. Just pi k is equal to 2. That is the critical temperature. Okay, now, so that argument works for 2 dimensions. Sorry, 2 components. Now, you can ask the question, all right, what happens? We know that when the number of components goes to infinity, that there is no phase transition, because this is the so-called 2-dimensional spherical model, and we know that in 2 dimensions, at least with short-range interactions, the spherical model has no transition in 2 dimensions. Now, of course, in the 2-component case, you can argue that these defects, or these vortices, are topological defects. And so the different topological sectors are characterized by 2 integer numbers, depending on the because if you put your system on a torus, and if you walk around the torus, in one direction, or there will be a topological number as of an integer associated with that direction, and if you go around in the other direction, there'd be another topological number, integer topological number, and so different sectors of the theory can be characterized by defining what these topological numbers are. And we argued that because of energetic considerations, that there's likely to be a phase transition between the topological sector, one topological sector, and another topological sector. Now, in the Heisenberg model with 3 component spin, the question is, does the same sort of thing happen? And in two space dimensions, for this n equals 3 system, there's a single topological invariant number, which I call n here, which you can you can write down as this silly, complicated-looking thing. But all this is the number of times. This gives a mapping of the space onto the surface of the unit sphere, when the invariant measures the number of times the space, the order parameter, the space of the order parameter encloses the unit sphere. Now, this invariant is of no consequence in statistical mechanics because the energy barriers. Now, remember that the topology itself is actually of no physical consequence without asking questions about the relationship of the topology to the physics. And in the two-dimensional Heisenberg model, this topological number defining different topological sectors is of no significance in statistical mechanics, because the energy barriers separating configurations, the different values of the topological invariant n, is of order unity. And therefore, there is no barrier between different topological sectors, which implies that transitions can take place at finite temperature and thermal equilibrium, and therefore there'll be no ordered state ordered in any sense for this two-dimensional 3-component Heisenberg magnet. Now, this was later proved, I suppose you can say, by Polyakov in the mid-1970s using a clever renormalization group. Now, let's go back to our vortices. So here's a picture, the theorist picture of an n equals 1 vortex, where we're gonna. Now, I have a circulation. That's the blue arrows going round and round, where I have a change of phase as I go right round the center of the vortex of, say, plus 2 pi. Now, the blue blob in the middle is supposed to represent the vortex core. And this vortex core must be normal fluid. Why is that? Well, it's very simple. You see, if you think about a vortex, say centered at the origin, and you calculate the velocity of the flow going round this central point, well, the velocity is proportional to 1 over the distance out from the center. So the velocity would diverge at the center of the vortex. But we know from earlier work, experimental or theoretical, that that if the superfluid flow velocity gets too big, the system simply goes normal. And so this vortex can't be superfluid everywhere, because if it were, the superfluid velocity near the center of the vortex would basically blow up. But it can't, and so the center of the vortex must be a region of normal fluid. Now, of course, in principle, one could make this quantitative, but it's not, fortunately, it's not necessary. And so our description, the description of the system we used was that the description of vortex is simply, we associated some extra energy with the core of with the vortex core. Now, let's ask the question, these vortices, why are they so important? Now, let's think about a two-dimensional system, and let's suppose that the superfluid is flowing with a uniform velocity u sub s between the two straight lines here, which represent the edges of the system. And let's suppose this flow velocity is, so the superfluid flows without friction, and therefore this flow will simply go on forever. Will never decay. So the question one has to ask at this point is, what can destroy the superfluid phase? Okay, so we set up a system at low temperatures, and we know that, and let's assume that it flows with no dissipation. So it flows with some velocity u sub s, superfluid velocity relative to the substrate. What can destroy this? Well, local excitations can't do anything. Because local excitations, little blobs of regions where the fluid goes normal, are not going to affect the superfluid flow. And so they can't make the superfluid fluid velocity decay to nothing like a normal fluid. And the only way that this flow can decay is by the reduction of the phase difference of the order parameter, or incidentally, using this idea that this system is described by a complex field, psi, mod psi ETI theta. This is the only place where we use quantum mechanics, because the superfluid order parameter quantum mechanically is simply defined by a complex field. That's the only quantum mechanics we use. So we just use the fact that this system is described by some complex field with an amplitude and a phase. And the superfluid velocity is just Planck's constant divided by the helium mass of the helium atom times the gradient of the phase. And so, now this uniform flow, the only thing that can unwind the phase difference between the top of the slide and the bottom is by a pair of a vortex and anti-vortex. A vortex, say, is the flow going round and round in, say, a counterclockwise direction, and the -1 vortex corresponds to a flow going round and round the opposite direction. Now, the only way this phase difference between the top of the slide, the bottom of the slide, which corresponds to the superfluid velocity, the only way this phase difference can be unwound is for a pair of vortices to be created somewhere, pair of vortices close together, and then if the one vortex goes say left and the other vortex goes right, so that this vortex pair will simply get further and further apart, and then eventually go to the system of edges. Or if this represents the outside of a tube, So if this pair go right round the system and annihilate at the back, this process will unwind the phase by 2 pi and will reduce the superfluid velocity. And if this process happens over and over again, for some reason, eventually the superfluid velocity will be reduced to 0. And that means the flow is dissipated. Okay, so this very qualitative hand-waving argument has the following important conclusion. A superfluid phase, the superfluid flow velocity will be at least metastable. If not stable, it will be metastable. And in order for this flow to be stable, this process of the vortex, this vortex pair suddenly appearing and then going round the system and then annihilating at the back and reducing the superfluid flow, that can't happen. Okay, because if it does happen, the superfluid flow decays, you know, you get 0 velocity, and therefore a superfluid phase will be characterized by the absence of these vortices. If these vortices are present in thermal equilibrium, and you try to impose a superfluid flow onto this, there'll be a concentration of free unbound vortices, and so the superfluid flow will be unstable. And therefore, the difference between the two phases, a superfluid phase and a normal phase, will be characterized by the presence or absence of vortices in thermal equilibrium. Okay, so this was the idea. And so at least at this point, one has something to hang one's hat on, in that it seems that the important physics of this two-dimensional superfluid system is described by a system of vortices in 2 dimensions, and the properties of the system will be characterized by the properties of this collection of vortices in thermal equilibrium. And so that was the problem that we approached. We investigated. Now, I was sort of, now let me just quickly say something. Thouless was basically, I think the only way I could describe him was he was a genius. Thouless was a person who understood everything about everything. He was also a very good mathematician. And so he was a person who is an amazing person to work under. And when I was working with David, I really started enjoying doing physics and got really motivated. And so I eventually, after much work, I managed to solve this problem. And the paper which really was vital to what we did was a paper that Thouless sort of threw at me during a conversation, a set of papers by his friend Phil Anderson and his students Gideon Yuval and so on. And what they'd done was they'd actually invented a clever renormalization group And they did their work before the work of Ken Wilson, who was really credited with having invented the renormalization group. The calculation that Anderson-Yuval did for the one-dimensional 1 over r squared Ising model was Anderson called poor man's scaling. But actually what they'd done was they actually invented a renormalization group procedure. And of course, being young and energetic and rather stupid, I sort of decided that this paper of Anderson-Yuval was something that was worth understanding and learning about. So I spent something like 6 months or maybe a year doing nothing but sitting at my desk, reading and rereading this paper and trying to reproduce the calculations. Eventually, I managed to do it and managed to reproduce their calculations. And then I thought, this is clever. This is an ingenious way of doing the problem. And maybe I can modify what they did and apply it to the two-dimensional system of the system of vortices. And eventually it worked out. But of course, doing something for the first time, as usual, I did it in the most complicated way known to mankind. And it was later made much easier. That it was done in a way that normal mortals could understand by David Nelson and Bert Halperin at the time at Cornell. And so let me just summarize the results. Now, this rather busy slide here summarizes our results. Now, basically, what it is the important quantity to look at is the momentum correlation function. This, G alpha, G sub beta of Q. That's the Fourier transform. And you can write this as some A, coefficient A, which depends on Q squared, times Q alpha, Q beta over Q squared, that's the longitudinal part, plus a coefficient B times the transverse projection operator. The important physical quantity is the measured or renormalized stiffness constant, this K sub R. And this is proportional to the measured superfluid mass. Of course, in here, the superfluid, two-dimensional superfluid density, rho sub S of R. R simply a symbol meaning renormalized or measurable, which would be a function of temperature. And this is divided by m squared kBT. And this quantity one can show is the limit as Q goes to 0 of the difference between the longitudinal part and the transverse part. And this stiffness constant proportional to the so-called superfluid density, which is just a quantity which just happens to have the dimensions of mass per unit area. And really, this second line here, maybe I missed out a Q squared. I don't think so. Could really be regarded as a definition of the stiffness constant or the superfluid density. Now one can calculate this quantity by a perturbation expansion in the density of vortices. Suppose this n is the vortex density, or the vorticity, if you wish. And this K sub r of t, this measured, in principle, measurable experimentally, in principle, but it's a fully so-called renormalized quantity. But this can be computed by perturbation expansion in the density of vortices. And it is given by this crazy looking formula on the third line. And it's basically it's basically proportional to the vortex correlation function. But this is not a hard quantity to calculate, at least the lowest order. It's an expansion in the density, basically as an expansion in the density of vortices. And so this quantity, it's easier to write in real space. This can be written as in real space by this formula on the third line, where this vortex correlation function, this n of r, n of 0, is easily calculated because you're calculating it as an expansion basically in expansion of the number of vortices present. And of course, the lowest number of vortices present is 0. The next term is simply one of these n's being plus 1, the other n being minus 1, and so on and so forth. And so this correlation function, this n of r, n of 0, you can calculate it as an expansion, as a power series in the vortex fugacity. And the vortex fugacity is just, the fugacity of one vortex is just e to the minus the energy of the core, this normal junk in the middle of the vortex, divided by kT. That's the so-called Y0. And so if we've simply got one plus vortex present, one minus vortex present, so this n times n is minus 1. It's got a minus in front, because one n is positive, the other is negative. So we get minus 2y squared times the separation, this r to the minus 2 pi k0, plus higher order terms, y to the 4th term, a y to the 6th term, plus etc., etc., etc. Okay, now if one makes the assumption that you can truncate this expansion at lowest order, in other words, just the y squared term, and you can worry about whether this truncation is accurate or not at a later point. It's easy to write down write as the inverse of this renormalized correlation function, this formula on the third last line. Now, actually, this formula actually contains, in a simple-minded way, all of the physics, because one can convert this formula valid to lowest order and this fugacity into so-called renormalization group equations. So, and the renormalization group equations simply are, you say, okay, suppose that I, increase my lattice spacing, or my microscopic cutoff, which I call little a here, and I call e to the L, e to the power of this parameter L as simply equal to R, the separation of the vortice, divided by the microscopic cutoff, or if you like, the lattice spacing. Then one can, after a little bit of calculation, one can convert this rather simple looking formula into two differential equations for the inverse coupling constant, remember that this correlation function, this K sub R, this is a physically measured quantity. And therefore, fiddling around with some microscopic cutoff can't change that quantity, but it can change this parameter, this bare parameter, this K naught, and it can also change this fugacity, this Y naught. And so, after a little bit of calculation, or a lot of calculation, one can write down these two so-called renormalization group equations, which give you how these effective coupling constants behave as a function of this parameter L. And so dk, the minus 1 by the L is just 4 pi cubed y squared plus terms of order y to the fourth, and dy by dl is 2 minus pi k times y plus terms of order y cubed. And so in the next slide, I give a graph of k on the horizontal axis versus the fugacity y on the vertical axis. And these flows, these lines, tell you how k and y are related as L increases with the arrows in the direction of increasing L. Now, you ask yourself, okay, what does this mean? Okay, well, a physical system, okay, now, of course, this is a bit of an assumption, and we're assuming that our physical system is parameterized by some value of k and some value of y, which you call k naught and y naught. And this will correspond to some point on this, on this diagram in this ky space. So let's think about a physical point starting somewhere in the bottom right-hand corner. Then you see as I increase the cutoff, as this parameter L increases, the values of k and y follow one of these lines. So we get an new effective theory. And as L goes to infinity, this parameter L gets larger and larger. The fugacity y starts getting smaller and smaller, and eventually y goes to 0. Okay, fine, that's just a piece of mathematics. However, if we start with some different values of k and y, for a particular k and y, k naught and y naught, you see that there's a particular line, it's a straight line that simply flows into the y equals 0 point at some k between 0.6 and 0.7. And this line separates two very different behaviors of k and y. We notice that if we start with a y and a k, somewhere in the right-hand half of the diagram, but we notice that if the fugacity starts off being large enough, that eventually the flow goes to, starts going parallel to the straight line and gets the effective fugacity, or the probability of vortex being present, gets smaller and smaller, but then eventually turns around and starts increasing. Okay, so next question is, how do you interpret this? Well, it's actually not difficult. You see, if you start from a system described by this k and y in the lower right-hand corner, eventually, under the scaling process, this fugacity goes to 0. which corresponds to an effective system with no vortices present, because if the fugacity is 0, the probability of a vortex being present is 0. And this corresponds, of course, to a system where the flow is not dissipated, because the only possible mechanism of dissipation is the presence of vortices. But if there are no vortices, there's no dissipation. Therefore, one has to interpret such flows as being below, as being correspond to superfluid phase, or if you like, below TC. If, on the other hand, the fugacity turns round and gets larger and larger, and goes to the situation where the fugacity is just increasing, and then, of course, the perturbation expansion breaks down, so one can't continue. But then you can say that since the fugacity is getting bigger and bigger, this obviously corresponds to a phase where there are free vortices present. And free vortices present means that it's not superfluid. So basically what we have here is we have a situation where we can distinguish the low temperature superfluid phase and the high temperature normal phase. And of course, the straight line simply corresponds to being at TC. And so we have a critical value of the K, which depends on the value, the initial value of Y. Okay, so this theory is a little bit strange, to say the least, but the interpretation is that the bottom right-hand corner of this diagram corresponds to T minus TC divided by TC as being negative, in other words, below critical temperature. And the rest of the diagram, where the fugacity flows eventually to larger and larger values, will correspond to a normal phase where you've got free vortices and therefore dissipation, therefore non-superfluid. So this diagram is a central, basically contain all the physics of this superfluid transition. And of course, here are some of the predictions. The first one is that the normalized stiffness constant, the measured stiffness constant, of course, depends on the physical values of K and Y, or otherwise known as K naught and Y naught. But this is equal to the effective, the same quantity in terms of renormalized K and Y. And so this is a very important renormalization group prediction. Then so in other words, then jump to the second line from the bottom, then what this says is that, you've got all these, Planck's constants and helium atom masses and so on, times the renormalized measured superfluid density, which is just a quantity that happens at the mass per unit area. And this is equal to the renormalized stiffness constant as a function of the physical parameters K naught and Y naught. But this is equal to the same quantity calculated in terms of what I call K infinity and Y infinity, which means the values of K and Y at L equals infinity. But if I'm below this TC, Y infinity is 0. Because the fugacity flows to 0. But then this renormalized stiffness constant, Kr, is just equal to the value of the parameter K. But K infinity, from the equations we calculated, is just equal to 2 over pi plus some constant times the square root of the magnitude of the deviation of the critical temperature. That should be the square root of mod t for t negative. And therefore, when you approach the critical temperature from below, when this little t goes to 0 from below, this combination of measured quantities is just equal to 2 over pi. In other words, the superfluid density, the measured superfluid density just below Tc, divided by Tc, is equal to this combination of fundamental constants. 2m squared times Boltzmann's constant divided by pi h bar squared, and this is equal to 3.49 times 10 to the minus, should be 10 to the minus 9 grams per square centimeter per degree Kelvin. And that is a crucial prediction of this theory, because that number, this 3.5 times 10 to the minus grams per square centimeter per degree Kelvin, is an inescapable number of the prediction of the theory. Fiddling around with the theory cannot change this number. And so this number, which is basically in principle experimentally measurable, is a smoking gun prediction. Because either experiment measures, when experiment measures this number, and if they come up with the same number as we predict, then the theory at least works. If, however, experiment comes up with a different number, then the theory falls apart, because there is no way that within our theory of changing this number. And so the question is, what are the predictions? Well, the experiment was finally done a few years later, and it was published in Physics Letters, volume 40 in 1978. It was done by Dave Bishop and John Reppy. And we have here two curves. The one curve is a line which starts off positive and then eventually falls to 0. That is basically this correlation function, superfluid density. But remember, this experiment has to be done, can't be done at 0 wave number and 0 frequency, because the theoretical prediction is for the correlation function measured at 0 wave number and 0 frequency. But that's not measurable, because the experiments are done, remember, it's about superfluid flows. So the experiment is done necessarily, if you got a resonant oscillating torsional oscillator experiment, that's done at finite frequency. And the frequency that you can do it at go down to about 10 hertz, but if you put in numbers, even 10 hertz is a large frequency compared to a characteristic frequency. It's actually a high frequency measurement. And then, of course, you've got this dissipation curve. The other curve with this sharp peak. And one would associate the peak at sort of as being roughly the critical temperature, because that's where you expect the dissipation to be a maximum. Now, of course, one has to somehow extrapolate these measurements back to 0 frequency and 0 wave number. And really, to do that, you need an extension to dynamic theory. And this was done by Ambe, Gauker, Nelson, Halperin, and Sidja, AHNS to be precise. And they managed to, using those results, we can extrapolate back to 0 frequency zero zero superfluid velocity. And so the dashed dotted lines are the theoretical prediction, the extrapolation back to compare with the theoretical measurement, or the theoretical prediction. And remember, the theoretical prediction is that the superfluid density, as defined as the correlation function, has discontinuity at the phase transition. And it jumps from a certain value down to zero as you go through TC. And the extrapolated theory actually agrees rather well with the predictions. So you can regard this as a verification of the theory. And so here is a summary of a number of the, of various experimental predictions of the superfluid density divided by, as you approach TC, divided by TC. And it's a set of different experiments done by different groups, some third sound measurements, and these torsional oscillator experiments, and there's this collection of points, symbols here on this picture are the results of all these different experiments. We're plotting the superfluid density per unit area just below TC times 10 to the 9. Not 10 to the 8, but 10 to the 9 grams per centimeter squared against the values of the critical temperature as a function of in Kelvin. And we notice that these cluster points look suspiciously as if they're clustered around a straight line. And if you simply draw the straight line correspond to the theoretical prediction, that straight line is exactly the line drawn according to the Kosterlitz prediction, which is quite a remarkable agreement between theory and experiment. As apparently the experimentalists had their points before they knew about the theoretical prediction. And so the theoretical prediction was drawn after the experimental points, and this is the result. So it's an amazing agreement between theory and experiment. Now, okay, so let me just quickly mention this. One could also apply the same sort of theory to the problem of the melting of a two-dimensional crystal. Now, you may say to yourself, but you can't realize two-dimensional crystals. But actually you can. And this was done by Georges Marais and co-workers who put polystyrene spheres onto the surface of a water droplet and measured various quantities like correlation functions by simply recording the positions of the polystyrene spheres with a CCD camera and analyzing the data at leisure. And let me just show you the slide. Let me skip through this. Okay, so here are the results of their measurements. There's few experiments. There's one about electrons and helium. There's another one but with the colloidal system. And of course, the colloidal system has got the colloids interact with long-range interactions, proportion of 1 over the distance cubed. And this is perfect for comparing theory with experiment, because one can actually show that these long-range interactions, the so-called KTHNY, standing for Kosterlitz, Thales, Halpern, Nelson, Young, theory is valid for these colloidal interactions. For short-range interactions, it's not valid, and your first order, the transitions tend to be short first order. However, for these colloidal systems, we have a set of experimental points, which are these points with rather large error bars. There's also some numerical results of some numerical simulations, which are the points without error bars. And then you have the theoretical prediction, which is this red curve, which seems to follow the experimental points rather well. Of course, it certainly follows the simulation points. But the prediction is that there is a discontinuity at the melting temperature of the so-called Young's modulus, which is some combination of elastic constants. And the theoretical prediction is that this is essentially 50 as you approach the critical temperature and below. And that's actually the red curve. And so the agreement between experiment and theory for this system, which is the same theory except more complicated as for superfluid helium. And so this is also, you can take this as confirmation of the theory. And then there was also some experiments done on where there was reasonable agreement in theory and experiment, but I won't talk anymore about that because I'm running out of time. So to the last slide is some acknowledgements, and I'd like to thank David Thowles. Unfortunately, David Thowles passed away, for introducing me to this beautiful problem. David Nelson for collaboration discussions. It was David Nelson and I really was the leader on this paper about discussing the universal jump in the superfluid density at TC, as you approach TC. John Reppy for many useful discussions, and of course the Nobel Committee for the recognition. And I'd like to thank my wife, Berit, for an amazing journey through life, taking us from Cambridge to Oxford, to Turin in Italy, to Birmingham, to Providence, and finally, but not least, my children, Carl, Jonathan, and Elizabeth, for putting up with their rather strange father. And so thank you very much for your attention, and I hope that you learned something from this talk. Thank you.
Thank you, Professor Kosterlitz, for a wonderful lecture. I hope all of us have really enjoyed your lecture for about an hour or so. So hope you will not mind in taking up some questions from the audience, if any. So
Sure.
I will request Professor P.R. Mahadevan to conduct the question and answer sessions and give the vote of thanks to Professor Kosterlitz afterwards.
So
Professor
why
Mahadevan.
no?
Yeah.
Yeah, so may I request anyone who has a question to please raise their hand so that I could coordinate.
So go ahead, please.
So Professor Kosterlitz, if you don't mind, you can come on your video now so that we all can see you.
Okay. Yep. Let me just
Yeah.
minimize this one.
Yeah.
Okay. I can see you. Can you see me?
Not yet.
No.
Okay. Okay.
We want to see you actually. Yes, we can. Yes,
Can you see me now?
yes, we can see you now. Right, great.
Yeah.
Yeah.
Yeah. I see GP. GP Das, could you unmute yourself if you can and ask your question?
So,
Yeah.
Professor Kosterlitz, it was a very beautiful talk. Now, I would just like to ask you about the similarity in the results that you showed for the polystyrene case along with the superfluid case. And you mentioned that the polystyrene case, the matching is better, but it is a more complicated system. So can you please elaborate on this? Why do you think that this is a more complicated system where the matching is better? Why?
Yeah, it's in principle not more complicated. It's just that the defects which control the phase transition, the melting of a two-dimensional solid, are dislocations.
Mm-hmm.
And if you like, of course, you're looking at the melting of a triangular lattice.
Mm-hmm.
And the dislocations are defined by Burgers vectors, and the Burgers vectors take on several values. And so the normalization group equations you end up, I mean, the theory is basically the same. It's a question of a theory of interactive dislocations. And these dislocations interact logarithmically, just like the vortices, but you've got an extra term, angular term.
Mm-hmm.
Now, this angular term leads to some pretty nasty technical complications. But otherwise, apart from that, the theory is basically identical, because in superfluid, the superfluid helium case is about the unbinding of vortices. In the crystal case, it's about the unbinding of these dislocations, which is technically, it's the same physics, but technically these dislocations are much more complicated. That's all.
Okay, thank you. Just one more clarification. So you mentioned in the beginning that the quantum mechanics is coming only when you are trying to understand the phase factor. Yeah, I mean, but
Well, I mean, the only thing that quantum mechanics says that we used is that the condensate order parameter is a complex field with a magnitude and a phase. That's it. That's the only bit of quantum mechanics we used.
Okay. Thank you very much. Yeah.
So it becomes equivalent to, in magnetic language, so n equals to a two-component spin.
Mm-hmm. Yeah.
Right.
Yeah. Okay. Thank you. Yeah.
Yeah. So I had a question regarding regarding the Heisenberg model that you spoke of, when you said that your topological excitations had no barriers, the different topological sectors that you had no barriers. So what would, one interaction we know is this magnetic anisotropy could lead to, or does it lead to the barrier?
Anisotropies make a lot of difference, of course, because suppose that the anisotropy is such that two of the three components are more strongly coupled than the other one. Then that becomes equivalent to the planar rotor model, because it's only the two most strongly coupled components that govern what happens which govern the fluctuations. And so the anisotropy is, of course, vital. But I was talking about a completely isotropic Heisenberg model.
Okay. And what would you and regarding the melting of the two-dimensional lattice, what would you think about the case of graphene, for instance?
Okay, right. The assumption that one makes is that the system can be described by a set of interacting dislocations in two-dimensional melting. And that's the only excitations one considers. Of course, the physical system is infinitely more complicated than that. There are many other things going on.
Okay.
But the assumption one makes is that, well, you ask the question, well, all right, we know that the melting will take, in two dimensions, will take place by these dislocations, the properties of the dislocations that will distinguish between an ordered phase and a fluid phase. It will distinguish between a phase with a resistance to shear and a phase with no resistance to shear, which you'd have to interpret as a fluid. And the excitations that control that will be dislocations.
Okay.
And then the theory of dislocation, interacting dislocations, you can work out. But the assumption is that it's a theory of dislocations and only dislocations. There's nothing else going on that's, if you like, relevant other than dislocations. And this assumption, it's just like the helium film. Our description is of a set of interacting vortices. Now, there are many other things that could be going on. And the hope is that everything else other than the vortices is, in the renormalization language, is irrelevant. In other words, their effects will disappear. Before as the transition is approached, where really only long-range fluctuations are important. That by the time you get to long length scales, those other effects have simply scaled away to nothing. Now, all these things are assumptions, huge assumptions, and the only, and basically, so one has to say, okay, you have a theory, and does the predictions of the theory agree with experiments? And as far as helium is concerned, the answer is yes. There is these flow experiments. The agreement between the theory and experiment is very good. And the predictions of the theory depend on the theory of interacting vortices. Now, within that theory, there is no way of changing the prediction as you approach the onset temperature. That's why I said that prediction is a smoking gun prediction, because within the theory you can't change that. And if the experiment can measure that quantity, if the experiment comes up with the same number, then the theory is correct with a pretty high degree of probability, in the sense that nobody's been able to change that prediction within the theory.
Okay.
That's what I meant by smoking gun experiment.
Sure. Okay. Yeah. And I guess, are there any more questions from the audience?
I'm sorry?
No, yeah, no, I asked if there were more questions from the audience.
Oh, sorry.
Yeah, yeah, so there is one.
Yeah.
So Dr. Shripati, could you please unmute
Yeah.
and ask? Yeah.
Yeah, thank you very much for your nice talk. Actually, I wanted to ask you how your studies are useful for other areas.
I'm sorry, I missed that. Something about other
Your
areas?
studies are, you have studied phase transitions. Whether this study can be applied to some other studies,
So could
other areas.
in other areas, could you comment on the generality? Yeah.
All right, well, the theory of superfluids can be
Application
translated
of your study
almost
into other fields.
directly.
That is what my question is. Application of your study in other areas.
Well, superconductivity, superconductivity in 2 dimensions is basically the same theory, except, of course, in superconductors, there's this extra length scale, the penetration depth, which acts as a sort of long distance cutoff. Now, but within the context of superconductors, for example, arrays in 2 dimensions superconducting Josephson junctions, the agreement between theory and experiment is also very good. The agreement is quite detailed, especially at finite frequency. Eventually, you see, you run into the problem that you have this finite penetration length, which is sort of maximum length scale at which the theory will apply. Eventually, if you go to larger length scales and there's penetration depth, that then the interaction between the vortices is too short-ranged, and so actually the system is, in principle, disordered at all finite. There's no, strictly speaking, there's no real transition in a 2-dimensional superconductor. But of course, experimental systems are limited in size. These junction arrays and stuff, you get an array maybe a few millimeters by a few millimeters. And so the theory works pretty well for such systems.
Okay. Yeah.
Although in principle, in an infinite system, there's no phase transition.
I see. Thank you.
Okay.
Yeah. So at the end, I'd like to propose the vote of thanks and thank Professor Kosterlitz for a relatively pedagogical introduction to his work, and thank you everyone else for being present here. And I'd also like to thank the EVLP team and our computer section for all the behind-the-scenes work in making this lecture successful. Thank you very much.
Thank you so much.
Thank you.
So from Professor Kosterlitz, we would like to send you the small memento for our lecture. So we'll mail it to your home address very soon. And wonderful meeting you. Thank you so much.
Thank you.
Thank you. Okay.
Very nice.
Okay, very nice. Okay, thank you very much again.
Okay, thank you very much.
Bye. Bye-bye. Okay.
Well, good luck, and I hope that everybody soon gets vaccinated against stupid disease that's going around.
Yes, we also hope so. And then, of course, if everything becomes normal, whenever you want to visit this India, you are very welcome, and we'll invite you to visit our center physically and interact with our students and faculty members. So it's an open invitation for you.
Right there. Yeah, I've actually managed to get my first shot of the vaccine, and I hope to get the second shot I'm supposed to get in a few days.
Oh, that's great.
Right.
We are still waiting for our turn.
Yeah, because I've been stuck talking to my computer screen for months now. You know, I'm a bit tired of being stuck in my so-called study at home.
Okay, so we are in a little bit better situation. We can say we are 90% normal for our teaching and research in the institute. That 10-15% probably in next few months. So it's a little bit better now in India, right?
Because I even find this remote teaching a lot of hard work. It's
Yeah,
much harder work than lecturing in person.
it's true. Right.
Right. Okay. Well, thank you very much, and
So thank you again. I mean, it's
goodbye.
wonderful to
Thank you.
interact with you. Yeah. Right. Thank you. Okay. Bye bye.